So the second speaker is Jokendra Nath Kundu. He would be talking on the doctoral dissertation titled as Self-Supervised Domain Adaptation Frameworks for Computer Vision Tasks. So I'll just quickly introduce Jogendra. So he's currently working as a research scientist at Reality Labs Research Meta, where he is involved in the development of eye tracking technologies for augmented reality and virtual reality applications. Prior to that, completed his PhD at IISc Bangalore, where he was advised by Professor Venkatesh Babu in the Vision and AI Lab. His research primarily focused on developing deep learning frameworks that improve the transferability of computer vision models in the absence of manual annotations. So he'll be speaking more about in his talk. Over to you, Jogendra.
Thank you for the introduction. Hello everyone. I would like to begin by expressing my gratitude to ACM India for recognizing my thesis as the runner-up for the ACM India Dissertation Award. So the recognition serves as a significant motivation for me to continue advancing my research in this direction. So today I'll provide a brief overview of my PhD work conducted at the Indian Institute of Science, which is titled as Self-Supervised Domain Adaptation Framework for Computer Vision Tasks. I don't probably need to tell how successful deep learning has been for various applications. Here I'll be focusing mostly on computer vision applications because that's the primary research area that I focused on. We know that computer vision deep learning has got a long point where we can detect different objects pretty accurately in various scenarios. So we can detect objects that are real people and also objects in cartoon scenarios. As long as we have training data, we can train models to do this as per our requirement. There has been a few challenges along the way, and the one that I would like to focus on is dataset bias. So dataset bias occurs when you have a specific dataset. For instance, you are training a computer vision model to detect pedestrians for self-driving car. You have collected some data, labeled the pedestrians using bounding boxes, and trained your deep learning model. It performs exceptionally well on the held out test set, which is derived from the same data set. However, when you deploy the same model on your car in a different environment, the results may not be as expected. For instance, the environment could be snowy with people with heavy coats, and which is a stark contrast from the training data set collected in different geographic locations. So visually, the new data set that the model is expected to label looks significantly different from the training data. This phenomena is also we refer to as dataset bias, and it can lead to issues such as missed detections or generally lower accuracy. Domain shift can occur in a variety of scenarios. I would argue that it's a phenomena that accompanies on every data set you collect. So let's consider a few examples to illustrate this point. One instance I have previously mentioned is that when you gather the data set on one city and aim to test it on a different city, let's say for semantic segmentation. Another scenario could be when you compile a data set from the web and then intend to deploy your model on a robot that captures images from its environment. In this case, factors such as angle, background, and lighting can significantly differ the leading domain adaptation. A particular common issue arises when we train models in a simulated environment and then aim to transfer them to real world scenarios. This is also referred to as sim to real domain shift and is prevalent challenge in the field of robotics. Okay, so can we collect more annotations to solve this problem? Often it is not practical to cover the visual diversity. For instance, to train a generic roads in segmentation model, one has to gather samples from different geographic regions, and city architectures varies quite a lot. So given the dynamic nature of the world and the immense visual diversity, constantly collecting new data and re-annotating it is not scalable. So therefore, we need to explore other strategies that can handle the datasets in a more efficient manner. So now I'll dive deep into the identifying challenges that are specific to the vision tasks. So broader vision tasks can be categorized into non-dense prediction tasks and dense prediction tasks. General ML classification and regression fall under non-dense prediction tasks. So non-dense prediction tasks can be of two types, image-like, for example, depth estimation and semantic segmentation, or non-image like such as 3D human pose estimation. Here the 3D human pose estimation though is a regression task, there is an underlying kinematic 3D structure, thus it is categorized as structure prediction task. So a crucial question that arises is in this context is why does task type matter? The answer lies in the need to reduce the risk of failure post-deployment. To achieve this, we need to impose additional constraints on the output space to reflect the natural prior distribution. Let us consider the example of pixel-level semantic segmentation. In this task, the model is required to assign a class level to each pixel in the image. However, without proper constraints, the model's predictions may end up violating our common sense prior knowledge. For instance, the model might predict car flying in the sky or grass on the road. These predictions, while technically plausible within the model's output space, are unrealistic in real world. Similarly, in case of 3D human pose estimation, the model is tasked with predicting the 3D coordinates of the key points in the human body. Here, the solution space must be constrained to ensure that the model's predictions adhere to the structural plausibility limits. For example, the model should not predict human pose where the arm and legs is bent in an impossible direction. So general domain adaptation approaches, which are primarily designed for image classification tasks, do not extend well for these dense prediction-based problems. This is because image classification involves predicting single class level for entire image, which is much simpler output space compared to the pixel level or 3D structural level predictions required in case of dense prediction tasks. In our work, we address this challenge by using generative models like adversarial autoencoders to impose prior enforcing constraints. So I'll dive deep into 3 of such selected works. In the first part, I'll discuss about one of our work, which is titled UM-Adapt. It's basically focused on domain adaptation for dense prediction tasks like semantic segmentation and depth estimation in a multitask setting. So here I explain the problem setting for multitask adaptation. So we have access to a source domain data containing images with the corresponding task output, which is typically extracted from a synthetic graphical environment. Whereas the target domain constitutes unpaired images sampled from natural deployed environment. The objective is to improve the performance in the target domain by adapting the knowledge from the source trained model. In this setup, we consider 3 related tasks such as depth estimation, semantic segmentation, and surface normal estimation. We formalize a novel idea to leverage cross-task coherency. So we introduce task transfer networks, where individual networks are trained to output representation of a particular task from a combined representation of rest of the tasks as input. For instance, the network on the top, depicted as nseg, takes output representation depth and normal to predict the other output representation, that is segmentation. This innovative approach allows us to leverage prior enforcing common sense knowledge, acting as a bridge between different tasks. Note that in this framework, we obtain 2 predictions for each individual tasks. Predictions that are output of task decoders regarded as direct predictions, whereas the predictions at the output of transfer networks are regarded as indirect predictions. To update the base model parameter, we employ 2 loss terms for each task, one at the direct prediction and the other at the indirect prediction. Such a setup does not allow a single task to dominate the training process, since the least performing task would exhibit high discrepancy and hence will be given more importance in further iterations. For adaptation, we make use of cross-task distillation. So let's look one such loss terms. Here, the energy term is computed as the discrepancy between the direct prediction and the indirect prediction of the same output. In an adversarial paradigm, nseg is trained to maximize the energy for the target while minimizing it for the source. And conversely, parameters of the target-specific encoder are updated to minimize this energy for the target samples. This adversarial training strategy ensures that as training progresses, the model fails to distinguish whether the input is coming from a source domain or target domain distribution. So the key takeaways of this work include the use of synthetic data to learn cross-task coherency-based prior enforcing mechanism, an innovative way to use cross-task distillation as an adaptation strategy, and the ability to generalize or adapt to multiple tasks at once. This work represents a significant step forward in the field of multitask adaptation, demonstrating the power of leveraging cross-task coherency and distillation for domain adaptation. So moving on towards better deployment, we developed learning techniques for privacy-oriented source-free domain adaptation. So conventional domain adaptation techniques assume simultaneous access to both source and target domain. So generally, the adaptation algorithms are designed to read samples from both source and target in concurrent fashion in order to minimize the feature-level domain discrepancy. However, in many practical scenarios, the source or the vendor and the target or the client may not be able to share their data with each other. This is often due to privacy concerns or regulations that protect sensitive information. So despite these restrictions, the vendor can still share a model that has been trained on the source data with the client. Now the client is faced with a new challenge. They need to perform source-free target adaptation. This means they must utilize the source-trained model without having access to the original source data to develop a model that is specifically tailored for the target data scenarios. So to address this practical domain adaptation scenario, we introduce a two-step approach called generalize then adapt. This approach involves specialized strategies for both vendor and client with the ultimate goal of improving the final adaptation. In the first step, the vendor aims to generalize. This involves training a source model that is not just effective for the specific source data, but also generic enough to be applicable to a wide range of unknown future clients. In the second step, the client aims to adapt once the client receives the generalized model from the vendor, and they aim to perform the target adaptation. The goal here is to leverage the shared source model to develop an effective target-specific model. So by combining these two steps, generalize then adapt approach provides a practical solution for domain adaptation, particularly for the source-free setting. Now we'll describe the vendor-side approach. Based on our analytic insights, we propose source-only multi-augmentation network named as SOMAN. SOMAN is a multi-head framework. The global head is trained according to ERM, that is using data from all the domains. And the kth live-on-out head is trained using data from all the domains except the kth domain. In the paper, we explain the reasoning behind such a framework, and I'll skip the details. We propose a method to select the most suitable head for the target dataset. This is done by choosing the head denoted by K prime that exhibits the lowest average self-entropy for the target data. This approach ensures that the model we use for the target dataset, one that is most certain about the predictions, thereby increasing the likelihood of accurate results. Okay, so note that we do not have access to target levels in this setting. Once we have identified the optimal head K prime, we combine it with CPI, that's a conditional prior enforcing autoencoder, to extract reliable pseudo-levels for the target dataset. This is achieved through a process known as confidence thresholding. So here CPI is equipped to infuse the common sense knowledge of how an output segmentation map generally looks like. That is, ensuring that car pixels are on the road and not flying in the sky, thereby reducing the failure modes and facilitating a constrained optimization framework. Next, we use the extracted pseudo-levels to perform self-training to obtain the inference stage model. Note that only a few selected weights are updated during the target adaptation process. So here I illustrate qualitative results of our work. The proposed vendor side and the client side modifications enable source-free domain adaptation with superior deployment performance against the state-of-the-arts. So moving on, we applied some of these concepts for more complex 3D vision tasks, such as 3D human pose estimation. Existing networks often exhibit unpredictable behavior when they encounter unfamiliar out-of-distribution data with no mechanism in place to disregard such samples. This can lead to inaccurate predictions and reduce model performance. To address this issue, we propose the implementation of self-adaptive pose estimation model equipped with the capability to estimate uncertainty. The model would not only make pose predictions, but also provide a measure of confidence or uncertainty associated with each prediction. So the pose predictions are generated by such systems should be accompanied with the uncertainty measure acting as a barometer of confidence, as illustrated on the right. It is important to note that for the second image, the uncertainty is at its peak for non-human samples, and it is at its minimum for samples where the full body is visible. This indicates that the model is more confident in its predictions for familiar in distribution, that is full body human samples, and less confident for unfamiliar out of distribution data, that is non-human samples. This uncertainty estimation capability can greatly enhance the reliability and interpretability of models' predictions. So in literature, the pose estimation architectures employ one of the following two design configurations. Localization-based representations employ fully convolutional architectures where the final pose is realized via heatmap-based spatial PDF. Such model-free designs do not allow to inculcate structural articulations or bone length priors. So structural articulation refers to a way different parts of the body move in relation to each other, while the bone length priors refer to the fixed proportion between different parts of the body. These are important constraints for the output space prior knowledge that can help to improve the accuracy and realism of pose estimation. On the other hand, regression-based representations employ fully connected layers to directly regress some form of 3D human pose. One can easily inculcate joint connectivity and bone length prior via model-based design with integrated forward kinematics. However, there is no provision to obtain joint level uncertainty as it sees the pose as a whole. So following this, the pose uncertainty can be quantified as the disagreement in pose predictions obtained through the two output heads subscribing towards two diverse design configurations. The pose uncertainty denoted as U of I measures the L1 distance between the pose predictions from the two heads represented as Q hat and Q tilde. This is visually represented in the figure. So in essence, this approach treats the difference in predictions from the two heads as a measure of uncertainty. If the two heads agree closely on the pose prediction, the uncertainty is low. Conversely, if the two heads produce significantly different pose predictions, the uncertainty is high. This provides a simple yet effective way to quantify uncertainty in pose estimation. Now, how do we train such model? The adaptation process accesses three different datasets. First, a labeled source dataset DS. Second, a dataset of background images DV to approximate an extreme out of distribution scenario. And third, unlabeled target domain samples DT. Following this, the adaptation process can be visualized through the pose uncertainty histograms. In the pre-adaptation stage, our goal is to enforce the desired behavior by maximizing the uncertainty U for background images that are representing out of distribution data, while minimizing it for the source data represented in distribution data. So this ensures that the model is confident about its predictions for the source data and acknowledges its uncertainty for the out of distribution background images. Upon encountering the unlabeled target, the adaptation process seeks to reduce the target uncertainty alongside a progressive self-training and set of reliable pseudo-levels. So note that the histogram of target uncertainties slide towards the source, implying the model now treats the target as in-domain samples. So following this, we develop a similar framework to quantify uncertainty at joint level. And this advancement provides a solid foundation to extend our adaptation process to work effectively on in-the-wild target domains. So this is particularly useful in scenarios where there may be external occlusions or truncated frame scenarios as shown in the video. So on the right, we present an illustration of a result where the size of the bubble indicates the level of uncertainty at each joint, similar to the parameter concept discussed earlier. So larger bubble size represents joints with higher uncertainty, while smaller bubble indicates joints where the model is more confident in its prediction. This visual representation provides an intuitive understanding of the model's confidence level at each joint. So in conclusion, I would like to summarize the key strategies I have explored in my thesis to tackle the domain set problem. So firstly, I have leveraged synthetic supervision. Synthetic supervision offers a wealth of labeled source data and output space. It provides its beneficials for developing generative prior enforcing mechanisms. However, it is important to note that synthetic supervision is not immune to domain shift. Secondly, I have explored the use of unlabeled visual data. In this context, we have investigated methods to utilize unlabeled data from the target environment through self-supervised learning strategies. This approach allows us to learn useful representations from the target data, even in the absence of labels. Lastly, I have enabled unsupervised domain adaptation. Under this strategy, we have delved into innovative learning techniques that can minimize the discrepancy between the labeled source and the unlabeled target. These techniques are specifically tailored to the computer vision tasks, as I discussed. So these strategies represent the core of my thesis and provide a comprehensive approach to tackle the domain set problem for a wide range of computer vision tasks. So here are all the publications that are part of the thesis but are not discussed in this talk. So please feel free to go over these if you have interest, learn more about this topic. The papers offer a more comprehensive understanding of the subject matter and could potentially spark new ideas or interesting research questions. With this, I would like to express my gratitude to everyone who has played a role, whether directly or indirectly, in my PhD journey. A special mention goes to my advisor, Professor Venkatesh Babu, for his invaluable guidance. As I look ahead, I'm excited about embarking on a stimulating research career at Reality Lab Research Meta. Thank you all.